The universe isn't just stars scattered randomly. It's more like a web, a structured web of light. This is the largest structure we know. Galaxies gather along these immense filaments. They don't spread out evenly. There's a pattern, and by the end, you'll understand the forces that designed it, the invisible pull of dark matter, the echoes from the Big Bang. There was a primordial blueprint. It dictated this intricate design. An unseen framework holds the threads together, and the empty vastness between them, that emptiness shapes everything we see. These answers, they rewrite our place. They change where we think we are. So what holds the true shape of the universe together? What do you think it is? That pattern is real. It's the actual architecture of the cosmos, a structure so large that galaxies look like dust in a light beam. That's the cosmic web. The largest single thing we've ever found. To see it, you have to step back, way back. Astronomers do that with massive surveys, the Sloan Digital Sky Survey. They don't just look at one galaxy. They map the positions of millions of galaxies, plot each one as a point in a three-dimensional map that goes on for billions of light years. And when you do that, when you step back from all those points, an image comes into view. It doesn't look like random glitter. It looks like a neural network. Or the froth of soap bubbles, or the structure of a sponge. That's the true skeleton of the observable universe. Inside this web, you can see its parts. First, the dense knots, the nodes. That's where galaxies crowd together in huge clusters, sometimes thousands of them, bound in a gravitational dance. Then there's the opposite, the cosmic voids, the empty deserts, vast regions between the threads. They can be hundreds of millions of light years across and hold almost nothing. And connecting the dense clusters, tracing the edges of those voids, are the filaments, the elongated bridges, the great highways where galaxies line up like beads on a string. This framework changes everything. It moves you from a child's drawing of stars on black paper to an engineer's blueprint of a cathedral. The universe isn't smooth. It's lumpy, it's structured, it's organized, and the existence of this design, written on such an impossible scale, puts one overwhelming question on the table. What kind of blueprint, etched at the very dawn of time, could dictate a form this grand? Gravity is the quiet architect. It's been drawing the blueprint of the cosmic web for over 13 billion years. The universe's master sculptor, working with the slowest, most deliberate hands, shaping the formless into the magnificent, but it didn't start with much. In the earliest moments after the Big Bang, the cosmos was a nearly smooth, hot soup of particles and energy, almost perfectly uniform, almost, and that almost is everything. There were tiny, random ripples in that soup, quantum fluctuations imprinted on reality itself, the faintest whispers of difference, microscopic spots where the density was slightly higher and others where it was slightly lower. The seeds, the universe's first imperfections, and gravity noticed. Gravity is an attractive force. It pulls things together. So over immense stretches of time, gravity began to act on those seeds. Matter in the slightly denser regions had a slightly stronger pull. That pull attracted more matter from the surrounding areas. As more matter gathered, the gravitational pull of that region grew stronger, attracting even more matter. A self-reinforcing cycle, a snowball rolling downhill for billions of years. Regions that started with a tiny head start grew into vast gatherings. The under-dense regions, meanwhile, were slowly emptied out. Their matter siphoned away toward the growing knots. This simple, relentless process of attraction is why matter in the universe clumps. The fundamental reason a perfectly even distribution was never an option. Gravity demands congregation. It pulls the scattered threads of the cosmos toward one another, setting everything on a long, slow collision course with itself. But if gravity only pulls things together, why do we see long, elegant filaments instead of just isolated blobs? What guides the flow of matter into such specific, thread-like paths? Those first marks weren't just random. They were a signature, a kind of blueprint set into the universe right at the start. To see it, you have to go back almost to the very beginning, a tiny, tiny fraction of a second after it all started, to something called cosmic inflation. And this wasn't the slow expansion we see now. This was something violent, a runaway stretching of space itself. The universe doubled, then it doubled again and again, over time spans so short we can't really picture them. It was over in an instant, but it changed everything because during that surge, something happened in the quantum world. At the smallest level, empty space isn't really empty. It's got these fluctuations, tiny, temporary wrinkles in reality. They usually just pop in and out of existence, but inflation stretched them. Think of a smooth sheet of rubber. If you stretch it fast, any tiny wrinkle on it gets pulled, magnified, frozen into a large pattern of hills and valleys. That's what inflation did. It took those quantum ripples and blew them up to a cosmic scale, imprinting them across the whole universe. Those magnified wrinkles became the first structures. Slight differences in density, a bit more matter here, a bit less there. That was the blueprint, the first set of instructions, written in the language of density, and gravity would spend the next 13.8 billion years following those instructions. These seeds decided where the first gravitational wells would be, where matter would start to flow, where the great cosmic web would eventually get drawn. But a blueprint is just a plan. It needs material and it needs a builder to become real. So what was it? What was the stuff that filled those cosmic valleys and started building? The stuff that gathered in those low points wasn't normal matter. It was something different, something we can't see. To make a structure as big as the cosmic web, you need a framework that's everywhere and strong and nothing like what we're made of. That's dark matter. It's the hidden structure. It's like, if you're going to build a great cathedral of light, you need the steel frame first, the dark scaffolding. That's dark matter. It's matter that doesn't follow the usual rules. It doesn't shine. It doesn't glow. We can't see it. For our tools, it's completely dark. The only way it talks to the universe, the only way we know it exists, is gravity. It has mass, so it pulls, and in the early universe, that pull was all that mattered. Because dark matter has this key feature, light pressure doesn't touch it. Back then, the universe was this hot, bright plasma, normal matter. The protons and electrons, the future stars, was being hit by intense radiation. Pushed around by light, but dark matter, since it's dark, was untouched. It could feel gravity's slow pull without getting scattered by the storm, so it started first. While normal matter was still a glowing, chaotic fog, dark matter began to quietly come together. It collected in those early density valleys from the blueprint. It made these huge, faint clouds, and inside them, an invisible skeleton started to form. A scaffold of gravity. That was the real foundation. Then the universe kept expanding and cooling, and normal matter finally caught up. The radiation faded, atoms could form, and when they did, they found they were already inside these deep gravity wells made by dark matter. They just fell like water finding the lowest point, down into those invisible valleys. The bright galaxies we see now, they didn't pick their spots. They formed where the dark matter put them. They're like bright decorations on a tree you can't see. So the big filaments of the cosmic web, they're not just lines of galaxies. They're the bright traces of something much bigger. They follow the densest parts of the dark matter underneath. Where we see a highway of galaxies, there's a huge, unseen river of dark matter flowing through space. It's gravity holding it all together. So when we chart the shining threads of the web, we're reading a shadow. We're seeing the outline of the real, dominant mass of everything. But if dark matter is the anchor, what's in the huge, empty spaces between the threads? What makes that sharp difference between the crowded filaments and the cosmic deserts? We have a way to test this history. We build universes inside computers. That's computational cosmology. It's changed how we understand things. We can't rewind time, but we can make a digital twin. Watch it grow. You start with a supercomputer. Give it a simple set of instructions. Begin with a nearly smooth, expanding box of space. Seed it with those tiny density fluctuations from the cosmic microwave background. Populate it with billions of particles, dark matter, normal matter, then set the rules. Let gravity act, let gas cool and form stars, let supernova explode. Press play, run it for over 13 billion years of cosmic time, compressed into months of calculation. The results are breathtaking. Projects like the Millennium Simulation, Illustris TNG. They've done this. You can watch the output as a movie. At first, it's a faint, cloudy haze, then gravity pulls. Structure begins to emerge. Tendrils of matter reach out and connect. Vast empty bubbles form. They grow. Dense knots of galaxies spin into existence at the intersections. The simulation doesn't just suggest a web, it builds one. Filament by filament, void by void, right before your eyes, and scientists compare these simulated universes to actual maps from galaxy surveys like the Sloan Digital Sky Survey. The resemblance is uncanny. The statistics match, the shapes align. The simulated cosmic web looks almost identical to the one we observe. This agreement is a profound validation. It tells us the basic ingredients in our recipe are essentially correct. The primordial blueprint, dark matter's scaffolding, gravity's patient work. We're not just telling a story, we're watching it play out in a digital laboratory. These simulations do more than confirm. They let us experiment. We can tweak the initial conditions. What if dark matter behaved slightly differently? What if the early ripples were stronger? Run the simulation again. See what kind of universe you get. Often the web falls apart or it looks nothing like our home. This process helps us rule out wrong ideas, zero in on the physics that shaped our reality. It turns cosmology from a science of observation into a science of creation. We learn the rules by building worlds, but even with this power, a simulation is only as good as the physics we program into it. And what happens when we look closer at the threads of the web? Find things our models didn't predict. The dark matter skeleton is invisible, but the cosmic web glows. So what paints the light onto that dark canvas? It's ordinary matter, the stuff we're made of, the gas that makes stars. That's the story, how the universe's hidden blueprint gets illuminated. After the dark matter scaffold was set, ordinary matter began its journey. Scientists call it baryonic matter. It was like a vast, diffuse ocean, hydrogen and helium gas filling the early universe. And gravity from the dark matter filaments pulled this gas. It flowed like water down a mountainside into those deep gravitational valleys. But this wasn't a gentle trickle. Streams of gas from different directions would meet inside the filament. They'd collide. The impact was violent. It created shock waves that heated the gas to incredible temperatures. Millions of degrees. At that heat, it doesn't shine in visible light. It glows in X-rays. So some of the cosmic web's filaments are these colossal, searing hot rivers of gas. Visible only to our space-based X-ray telescopes, they trace the dark matter's form with a faint, high-energy light, but not all the gas stays that hot. In denser parts of the filament, especially near where filaments intersect, the gas can cool. As it cools, it condenses. It fragments into vast, dense clouds. And inside those clouds, gravity takes over again, pulling the gas tighter until nuclear fusion ignites. A star is born, millions, then billions of stars gather, and a galaxy flickers to life. That's why galaxies line the filaments like pearls on a string. They form where the gas, following the dark matter's roadmap, finally settled and cooled enough to spark. Yet this process isn't one way. Star formation itself changes the game. This is a crucial idea. Astrophysical feedback. Massive stars live fast and die young. They explode as supernova. These explosions blast energy and newly forged heavy elements back into the surrounding gas. And at the centers of galaxies, supermassive black holes can become active, swallowing material and firing out jets of energy that can cross entire galaxies. This feedback is a cosmic regulation system. It heats up nearby gas, prevents it from cooling and forming new stars too quickly. It can even blow gas completely out of a small galaxy, shutting off star formation for a time. So the final luminous pattern of the web, which filaments are bright with galaxies and which are faint, isn't just dictated by dark matter. It's a complex dance. Dark matter's gravity draws the gas in. The gas physics decides whether it gets hot and faint or cools and shines, and the stars that form then push back. Their feedback shapes their own future. It shapes the brightness of their thread in the web. It's a continuous conversation between the invisible scaffold and the visible, dynamic stuff that lights it up. That interplay answers why the web isn't a uniform neon sign, but a tapestry of light and shadow, and it leads to the next question. If we could see this whole tapestry at once, what would it look like? What are we actually seeing when we finally map the light of the cosmic web? The universe has this dramatic landscape. You've got the brilliant, crowded filaments on one side, and then on the other, the profound, silent voids. They really define each other. The emptiness makes the structure visible, and the structure carves out the emptiness. The filaments are like cosmic highways, rivers of galaxies and superheated gas, places of constant motion. Galaxies are closer together there. Their gravity influences each other. They can swing past one another, sometimes merging in colossal collisions. Those collisions trigger bursts of new star formation. The environment is dynamic, rich with raw materials for building stars and solar systems. It's a bustling metropolis on a galactic scale. If you were inside a filament, the night sky would be spectacularly crowded, the soft glow of neighboring galaxies everywhere. Then you cross the boundary into the void. The contrast is absolute. Voids aren't just empty space, they're the emptiest places we know, spherical regions hundreds of millions of light years across, where you might find only a handful of lonely, isolated galaxies. The rest is near-perfect vacuum, a galactic desert of staggering scale. If our Milky Way were adrift in the center of a void, our nearest galactic neighbor might be so distant, so faint, that we wouldn't know other galaxies existed at all. The night sky would be almost pure black. This great divide isn't an accident. It's the inevitable outcome of gravity's work. Those initial ripples, the slightly denser patches pulled matter in. The slightly emptier patches lost it. That created a runaway effect. As matter drained from the underdense regions to feed the growing filaments, the voids were evacuated. Emptied out, they grew larger and more spherical over time, because gravity pulls equally from all directions toward the denser surrounding walls. The void is simply what's left behind. After the universe's material has been gathered up, it's the negative space in the sculpture. This dynamic creates a universe of extreme contrast. It's not a gentle gradient from crowded to empty. It's a sharp boundary, a cliff edge in the distribution of matter. The vibrant, structured web of light exists precisely because of these immense oceans of nothingness surrounding it. One cannot exist without the other. The void gives the web its shape. The web gives the void its meaning. That relationship raises a possibility. If the voids are so empty, what happens to the galaxies that do, against all odds, find themselves born within one? Mapping something mostly invisible, that was the real challenge. For a long time, the cosmic web was just a theory, a prediction from our models, but to confirm it, you had to see it. Not in a simulation, but out there in the actual sky, which meant looking in new ways. the most direct approach is to map the galaxies, because galaxies trace the densest parts of the dark matter filaments. So if you get the precise 3D location of enough galaxies, you can trace the web's skeleton. That's what big surveys did, like the Sloan Digital Sky Survey. They weren't just taking pictures, they used a spectrograph to capture each galaxy's light and split it into a spectrum. And in that spectrum, they looked for a specific signature, the redshift. The universe is expanding, so light from distant galaxies gets stretched to redder wavelengths. The farther the galaxy, the greater the redshift. By measuring that for millions of galaxies, astronomers could calculate their distance. Combine that with their position on the sky and you get a 3D map, a point cloud of the universe, and when you connect those points statistically, the web emerges. In these maps, the theory became visible reality. The filaments and voids were there, but galaxies are just the bright signposts. They're like cities on a map. What about the roads themselves, the vast, diffuse rivers of gas flowing between galaxies in a filament? That gas is called the warm-hot intergalactic medium. The WIM, and it's incredibly difficult to see. It's too hot to form stars, so it doesn't shine in visible light, but it is hot enough to glow in X-rays and in specific ultraviolet wavelengths. To find it, you point your most sensitive space telescopes at the seemingly empty spaces between galaxies in a filament. Instruments like the E-Rosetta X-ray telescope, scanning the whole sky in X-rays. Or Hubble, looking for faint ultraviolet absorption lines from the gas. It's like trying to see the heat haze rising from a desert highway from orbit. The signal is faint, buried in noise, but slowly, astronomers have begun to detect it. They've caught the X-ray glow from massive filaments connecting galaxy clusters. They've seen the ultraviolet fingerprints of the WIM in the light of distant quasars, shining through the cosmic web like a flashlight through fog. Each detection is a direct confirmation. The space between the shining beads isn't empty. It's the road itself glowing at 1,000,000 degrees. The quest isn't over. Future missions are being designed with the cosmic web as a primary target. The European Space Agency's Athena X-ray Observatory, launching next decade, will have the sensitivity to map the hot gas in filaments in detail. It will watch how galaxy clusters at the intersections of the web are fed by these rivers of gas. These aren't just bigger telescopes, they're new kinds of eyes tuned to see the hidden architecture, and every time an observation matches a prediction, a filament of gas right where the galaxy map said, an X-ray glow tracing the predicted curve, it's more than data. It's a connection, a dot connected across the void. It means the story we've pieced together, from quantum ripples to dark matter scaffolding, is true. We're not just imagining the skeleton, we're starting to see its shape. This grand map of everything brings us to a modern puzzle. One of the biggest questions in cosmology now isn't about what we see, but about the speed. How fast it's all moving apart, that's called the Hubble tension, and it might be tied to the cosmic web. The Hubble constant is just a number. It tells us the universe's expansion rate right now. The current speed of it. For a long time we thought there was one right answer, but then we began measuring it two different ways. One way looks back to the beginning. It uses the afterglow of the Big Bang, that cosmic microwave background, as a starting point. The patterns in that ancient light let us calculate what the expansion rate should be today. The other way measures it locally. We look at nearby stars and galaxies, using them as mile markers to gauge the stretch of space right around us. These are two independent methods. Checking the same number, they should agree, but they don't. The local measurements keep giving a faster rate, faster than the early universe prediction. The difference isn't huge, but it's stubborn. It stays there even as our tools improve. That's the Hubble tension. It points to a gap in our understanding. Either one of our techniques has a hidden flaw, or the universe is more complex than our model says. This is where the cosmic web enters. Could that vast, lumpy structure be influencing the measurement? When we measure the local expansion, we're not in a smooth, average universe. We're inside a specific neighborhood, the local group of galaxies sitting within a filament of the web. We are inside the structure. What if the dense environment of a filament with its strong local gravity and flowing matter changes how galaxies move? Or what if the pull from a nearby supercluster gives our local region a tiny extra nudge, affecting our speedometer? Maybe the properties of the filaments themselves, their thickness, their density, how matter flows introduce a kind of cosmic bias into our local view. It's like trying to measure the flow of a great river while standing in a turbulent eddy near the shore. Your measurement might not reflect the broad, smooth current of the main channel. Studying the web's detailed architecture, mapping not just where galaxies are but how they move within the filaments, could give us new data. It might show that tension isn't a flaw in our physics but a clue. A sign that the large-scale structure leaves a fingerprint on everything, even on how we measure its most fundamental behavior. That connection turns the cosmic web from a curiosity into a central piece of a modern mystery. Understanding why galaxies gather along filaments isn't just about charting a skeleton anymore. It might be the key to hearing what the universe is saying about its own expansion. And about what we might still be missing. This architecture doesn't just place galaxies, it sets them in motion. A galaxy spins, but that spin has to come from somewhere. A universe that starts as a smooth, expanding fireball, how does it create these whirlpools, billions of light years wide? The answer might be in the filaments themselves. Think of a river. Water flows downhill toward a lake, but if the riverbed is uneven with rocks and bends, the water doesn't move in a straight line. It swirls, it develops eddies. A similar thing happens on a cosmic scale. Vast rivers of dark matter and gas flow along the gravitational slopes of a filament, heading toward the dense cluster at a node. Their path isn't perfectly smooth. The surrounding geometry of the web, the pull from neighboring filaments, the shape of a nearby void exerts subtle, twisting forces. These are tidal forces, the same kind of pull the moon uses to create ocean tides, but operating across millions of light years. These forces don't just pull matter inward. They can torque it, give it a slight twist. That idea is called tidal torque theory. It suggests the initial spin of a galaxy, its angular momentum, comes from a cosmic misalignment. In the early universe, a collapsing cloud of matter would have had a certain shape, maybe slightly elongated. The gravitational pull acting on it from all the surrounding matter in the web would have come from a slightly different direction. That mismatch, that offset between the shape of the cloud and the direction of the pull creates a natural lever, a twist. As the cloud collapses under its own gravity, that initial twist gets amplified. Like a spinning ice skater pulling their arms in to spin faster. So the rotation of a spiral galaxy, with its arms sweeping around a core, might trace back to the gravitational nudges of the entire cosmic neighborhood when the universe was young. The specific way a filament was oriented, the location of the nearest void, the tug from a distant supercluster, all these large-scale features could have conspired to impart that first, faint spin. It's a profound connection. The largest structures, the filaments of the cosmic web, directly influencing one of the most fundamental properties of the galaxies that form inside them. This chain of cause and effect turns the web from a passive map into an active sculptor, shaping not just where things are but how they move. And if the web can spin galaxies, what other invisible influences does it have on their destiny? That faint glow in the filaments, it's more than just structure. It solves a cosmic accounting problem, a mystery of missing matter. We know how much ordinary matter should have been made in the Big Bang. The recipe is in the oldest light, but when we count all the stars, all the gas, all the dust we can see, it only comes to about half of what the math says should exist. For decades, the other half was just gone. Where was it? That's the missing baryon problem. Baryons are protons and neutrons, the stuff of atoms, and a huge part of the universe's baryons were unaccounted for. The main suspect was always this diffuse, superheated gas in the cosmic web, the WIM. Theorists thought this plasma, spread through the vast filaments and halos, could be hiding the missing ordinary matter. It wasn't missing, it was just incredibly hard to see, like trying to spot water vapor in cold air. You can't see it until it condenses into fog. The WIM is that cosmic fog, but at hundreds of thousands, even millions of degrees. At that heat, it doesn't shine in starlight. It glows faintly in X-rays, or it absorbs very specific wavelengths of ultraviolet light. Detecting it is a task of extreme subtlety. Astronomers use the brightest beacons as flashlights, quasars, the luminous cores of distant galaxies. By analyzing the spectrum of a quasar's light as it travels billions of light years, they look for tiny dips. Absorption lines like cosmic fingerprints. Each dip tells them the composition, the temperature, the density of the gas it passed through. It's finding the silhouette of the invisible by studying the shadow it casts. Piece by piece, this method is working. Teams have found evidence in the spectra of hundreds of quasars, building a statistical picture of these hot reservoirs. And with X-ray telescopes, they've started to see the faint, diffuse glow of the hottest parts of the filaments, especially where they feed into galaxy clusters. The story is coming together. The missing ordinary matter isn't lost. It's woven into the fabric of the cosmic web itself, a thin, hot plasma tracing the dark matter skeleton. This changes what the filaments are. They aren't just highways for galaxies. They are the universe's primary storage system for its ordinary atomic material. Vast reservoirs holding more atoms than all the stars and galaxies combined. Finding them completes a fundamental chapter in our cosmic inventory. It confirms the universe hasn't lost anything. It was all there, hiding in plain sight, in the architecture of everything. The universe remembers the path it took. That's the third thing. Galaxies aren't just scattered along the filaments. They're oriented by them, their shapes, their spins. They hold a memory of how they were built. It's like a tree's rings recording the seasons. A galaxy's structure can tell you the direction of the ancient rivers that fed it. And this isn't random. Astronomers have mapped it. They look at thousands of galaxies inside the cosmic web, and they measure their orientation, and they find a pattern. It's subtle, but it's real. For the most massive galaxies, the giant ellipticals at the dense intersections, there's a clear trend. Their longest axis tends to point along the filament they're in. It's as if the galaxy is stretched along the cosmic highway that birthed it. For spiral galaxies, the story is about spin, their rotation, the direction their arms sweep. It also shows hints of an alignment. Relative to the filament, in some cases, the galaxy's disk spins in a plane that's perpendicular to the filament. It's a more complex signal, but it's there. These alignments are faint, they're statistical. You only see them when you average over thousands of systems, but they're a fossil record, a direct imprint from the moment of formation. You think about how a galaxy forms inside a filament. Vast rivers of dark matter and gas flow along that gravitational valley, converging toward a knot. That flow has a direction. It's moving along the filament's spine. So when a giant galaxy forms at the crossroads, it's built from material arriving from multiple directions, but the dominant flow is along the main highway. That flowing motion doesn't just deliver mass, it delivers momentum. It can stretch the forming galaxy or set it spinning in a specific way, like a leaf caught in a stream. The final shape of the galaxy freezes that initial motion. For a spiral galaxy forming within a filament, not at a crowded intersection, the story is different. The gas might flow into the forming disk from the sides, from the thinner dimensions of the filament, that could set the disk spinning in a plane that aligns with the filament's width, not its length. The precise alignment depends on a complex dance of accretion, but the key is the large-scale environment leaves a mark. This discovery turns galaxies into cosmic compasses. By measuring their orientation, you can infer the direction of the ancient flows that assembled them billions of years ago. We're not just looking at a static map of the web. We're seeing the dynamic history of how it was built, written into the architecture of its brightest inhabitants. It confirms filaments aren't just backdrops. They're active construction sites with rules that govern how everything within them takes shape. And if the web structure can dictate the spin of a galaxy, what other transformations does it oversee? At its crowded central hubs, the first light in the universe wasn't a smooth glow. It sparked along these invisible threads. That's the fourth mystery, how the cosmic web built the first stars and galaxies. You have to look back to a time before time meant much. A few 100 million years after the Big Bang, the cosmos was dark and it was profoundly cold. The afterglow from creation had faded to a faint microwave whisper. The universe was just a sea of neutral hydrogen and helium gas, and it was laced through with the invisible scaffolding of dark matter. In that darkness, gravity had already been at work, drawing out the first faint filaments of the cosmic web. These weren't the majestic highways we see today. They were the ghostly precursors, tendrils of dark matter tracing the densest lines of that early blueprint. And where these tendrils crossed, or where they were thickest, the first knots formed. Small dark matter halos, gravitational potholes. These halos were the cradles. They collected the neutral gas from the surrounding void, but gas alone doesn't make a star. It needs to cool, to condense, to shed energy and collapse. In our modern universe, that's easy. Gas has trace amounts of heavy elements, carbon, oxygen, silicon from previous generations of stars. These elements act like a cosmic coolant. They radiate heat away efficiently, but in that first epoch there were no heavy elements, none. The universe was chemically pristine. Only hydrogen and helium. So how did the first gas clouds cool? Through a much slower, more fragile process, molecular hydrogen. When two hydrogen atoms bond into a fragile H2 molecule, that molecule can vibrate and rotate. It releases a tiny bit of energy as infrared light. It's a terribly inefficient coolant compared to modern metals, but in the deep cold and growing density of those first dark matter halos, it was just enough. A slow leak of heat. Over millions of years, that slow leak allowed the densest pockets of gas at the hearts of these halos to finally collapse under their own gravity. And when they crossed a threshold of density and pressure, nuclear fusion ignited at their cores. The universe saw its first sunrise. These were the population 3 stars. The first generation, they were nothing like our sun. Theory says they were monsters, behemoths, possibly hundreds of times more massive than our own star. They burned ferociously hot and bright. They lived for only a few million years before ending in colossal supernova. Their light ended the cosmic dark ages. Their deaths polluted the pristine gas with the first heavy elements. The ash from those first explosions was the seed for everything to come, and this whole process didn't happen in isolation. It happened along the filaments. Those dark matter tendrils acted as the universe's first irrigation system. They funneled fresh flows of neutral gas from the surrounding voids into the growing halos, feeding the birth of the first stars and soon the first protogalaxies. A single halo might form a few of these brilliant, short-lived stars, but gravity would pull halos together along the filament. They would merge, their stars would gather into a larger swarm. Gas enriched by the first supernova would cool faster, leading to more efficient star formation. So the filaments enabled a rapid assembly line, channeling material, merging structures, accelerating the birth of the first true galaxies. To test this story, we need to see it. And that's the mission of the James Webb Space Telescope. Its infrared eyes are tuned to look back to this epoch of first light. It searches for the faint, redshifted glow of those first galaxies. A key question it seeks to answer is one of arrangement. Do those earliest galaxies, seen when the universe was only a few % of its current age, also line up? Do they trace the faint, initial threads of the infant cosmic web? Early results are tantalizing. They show hints of elongated structures, galaxies aligned in ways that suggest filamentary patterns even at these incredible distances. Each confirmation would be a direct link, connecting the quantum ripples of the beginning to the dark matter scaffold, to the flow of gas, to the ignition of the first starlight. It would show the web wasn't a later development. It was the framework for the universe's very first cities of light. These cosmic highways, they don't last forever. They have a lifespan, a beginning, a middle, and an end. So the question is, what happens to one of these filaments over billions of years? Does it keep its shape or does it come apart? It comes down to a kind of tug of war, a battle between forces that build things up and forces that tear them down. For most of the universe's history, gravity was winning. It pulled matter into the filaments, made them denser, more defined, but there's another force working on the largest scale, dark energy. We don't know what it is, but we see what it does. It's making the universe expand faster, not just continue, but accelerate, and that acceleration changes everything for the cosmic web. You can picture the filaments like elastic bands stretched across these growing voids. As the space between galaxy clusters expands faster, those bands get pulled taut, they're stretched, and that stretching doesn't just move the clusters. It thins the filament itself. The rivers of gas and dark matter inside it become more diffuse. The traffic on the highway slows down. Over trillions of years, this could get so severe it severs the connection. A filament stretched too thin by the accelerating universe might just snap. The galaxy clusters at its ends would drift apart, isolated islands in an ever-growing sea of emptiness. The web would start to fray, but there's another force, a more violent one, reshaping filaments from the inside. The gravitational pull of the massive galaxy clusters at the nodes. These clusters are insatiable. Their gravity acts like a cosmic vacuum, pulling in matter not just from nearby, but from the filaments that feed them. They can siphon gas, even entire smaller galaxies, right out of the connecting threads. This process is called accretion, and it can drain a filament over time. Make it weaker, less populated. You see evidence of this. The filaments leading into the richest, most massive clusters often look thinner, more depleted compared to filaments connecting smaller groups. The biggest cities are consuming their own supply lines. So the life cycle of a filament is a story of competition. It forms from the gentle collapse of matter along a dark matter ridge. It grows and strengthens as gravity feeds it for billions of years, but eventually the tides turn. The accelerating expansion of space starts to pull it apart from the outside. And the greedy clusters at its ends consume it from the inside. In our current universe, we're probably seeing the cosmic web at its peak. A mature, intricate structure, but one that's begun a slow, inevitable decline. The fate of the filaments is tied to the ultimate fate of the universe's large-scale structure. As dark energy's influence grows, the web will get more diffuse. More fragmented, the great cosmic metropolis will slowly empty out. Its connecting roads will fade into the void. This isn't a fast process. It happens over timescales that dwarf the age of our solar system. But it points our gaze to the far future, to the fundamental forces that will decide the final architecture of everything. But gravity and gas don't tell the whole story of the filaments. There's another invisible actor in the cosmic web, magnetic fields. Their presence is a profound mystery. They're whispers of force in the near emptiness between galaxies. How do you find a magnet in a void? The fields out there are unimaginably weak, billions of times fainter than a fridge magnet. Detecting them across millions of light years seems impossible. But we have clues there, woven into the filaments themselves. The question is where they came from. One idea points to the universe's infancy. Tiny magnetic seeds could have been generated in the chaotic plasma of the early cosmos. Another source is closer to home, or closer to every home of light. Inside galaxies, magnetic fields are created and amplified by dynamos, the churning motion of charged gas in stellar nurseries around black holes can build immense magnetic structures. And galaxies, especially active ones, can act as cosmic exporters. They can blow these magnetic fields out into intergalactic space through colossal winds. Imagine a dandelion releasing its seeds on a breeze, but the dandelion is a galaxy, and the breeze is a million-degree hurricane of particles. These expelled fields travel along the paths of least resistance, the filaments, spreading a faint, ghostly magnetism through the vast rivers of the warm, hot intergalactic medium. What could such a faint field do? Its strength is negligible compared to gravity. It won't pull galaxies together, but it doesn't need to. It works on the small stuff, on charged particles. The gas in the WIM is a plasma, a sea of electrically charged particles. Even a weak magnetic field can guide these particles, influence how they move and collide. It could help stabilize the thin gas against dissipating into the void. It might even dictate how that gas eventually cools and condenses to form new stars. And there's another traveler affected by these fields, cosmic rays. Atomic particles accelerated to nearly light speed by supernova and black holes. As they journey, magnetic fields act as invisible guide wires, bending their paths. The filaments could be magnetic highways for these high-energy particles, channeling them across the cosmos. If we could trace a cosmic ray back to its source, its twisted path might map the magnetic field lines of the web it traveled through. Proving this is the next frontier. The hunt is on for ways to see this invisible ink. One method looks for a specific kind of light. When light from a distant quasar passes through a magnetized medium, its polarization can rotate slightly. An extremely subtle effect called Faraday rotation. By measuring the polarization of light from thousands of background sources, astronomers can piece together a map of the magnetic fields in the foreground filaments. It's painstaking work, like trying to discern the shape of a glass sculpture by studying faint distortions in the landscape seen through it. Another clue might come from synchrotron radiation. If electrons are spiraling along these vast magnetic field lines, they should emit a faint radio whisper. New generations of radio telescopes are listening for that hum. To find these fields would be to uncover a new layer of physics in the cosmic web. It would show the universe's largest structures are not just shaped by mass and gravity, but also by forces born in the hearts of galaxies and stretched across the void. It adds a dimension of connection that is not just gravitational, but electromagnetic, a silent, pervasive influence on the traffic of matter and energy that flows along the great dark roads of everything. The most violent things in the universe are connected to its biggest structures. Almost every galaxy has a supermassive black hole at its center, a place where gravity is so strong light can't get out. But they're not just holes, they're engines, and what powers them, what makes them grow, is the shape of the universe itself. It's a kind of loop. The large-scale structure sets up the conditions that then control it. You have to think about where these black holes are. They're in galaxies, and galaxies aren't just placed anywhere. They follow lines. They gather where those lines cross. That's where things are most crowded, where you get a node, a whole cluster of galaxies, hundreds of them all together. In a place that dense, galaxies are going to interact. They'll pass near each other, their gravity pulling them into a spiral until they merge. When galaxies merge, it's chaos. Stars get sent into new paths. But the important part is the gas. Huge clouds of it crash together, and that gas gets pushed. It's driven inward toward the very center of this new, bigger galaxy. Right to where the black hole is. It's a sudden, enormous delivery of fuel. the black hole starts pulling in material fast. As that gas falls in, it doesn't just vanish. It forms a disk, a hot, bright disk of plasma. The friction heats it up millions of degrees and it glows. It can outshine billions of stars. That's an active galactic nucleus. And one of the brightest things we see, but it's not just about the light. The process can also create jets, beams of particles shooting out from the black hole's poles, almost at light speed. These jets can go incredibly far, way past their own galaxy, and this is where the large-scale structure gets affected. Those jets, that radiation, they blast into the surrounding filament of the cosmic web. They heat up the thin gas that exists in that thread between the galaxies. By heating that gas, the AGN stops it from cooling. It prevents that gas from collapsing to form new stars. Not just in its own galaxy, but in other galaxies nearby too. It's like a thermostat. A single active black hole at a crossroads in the web can influence star formation across a huge region. So you get this cycle. The dense environment of the filament causes galaxies to merge, which feeds the black hole. The black hole turns on, becomes active, and heats the gas in the filament. That heating then suppresses more galaxy growth along that same thread. It regulates itself. The structure creates the engine, and the engine then shapes the structure. Without that, the filaments might make stars too fast. The universe would look different. The cosmic web isn't just a backdrop, it's an active system. And the black holes are like transformers in that circuit. They take gravitational energy and turn it into feedback that sculpts the cosmos for billions of years. There's this question about the cosmic web. A filament could be there, but no one sees it. Not because it's empty, because it's made of something we can't see. Could you have threads that are completely dark, pure dark matter filaments connecting clusters but with no galaxies, no hot gas, no light at all to mark them? That idea isn't so strange. Our whole picture of the web is based on tracers. We see the glowing signposts, the galaxies, and we infer the dark matter road underneath. We detect the faint X-ray glow of hot gas and map the filament it's flowing through. But what if, in some places, that process broke down? Imagine a dark matter filament that formed like any other from that early blueprint. Gravity pulled the dark matter into that long, dense river, but for some reason the ordinary gas never followed. Maybe local conditions were wrong. Maybe the gas was heated by radiation from an early quasar, so it couldn't cool and fall into the gravitational well. Or it was stripped away by something violent long ago. The result would be a ghost road, a cosmic highway built and ready, but with no traffic, no streetlights. A pure dark matter structure tracing a path through the void, invisible to every telescope we have. Dark filaments would challenge our maps. Everything we think we know about large-scale structure assumes light traces mass. That where we see galaxies, there's dark matter underneath. But if dark filaments exist, that relationship isn't perfect. There would be mass without light. Our maps of the cosmic web, woven from points of starlight, would be incomplete. They'd show the bright threads and miss the dark ones. The universe would have a hidden architecture, even beyond what we've already found. So how do you find something that emits no light and doesn't interact with it? You'd have to catch it bending space itself. That's where gravitational lensing comes in. A massive object like a cluster bends light from behind it, a cosmic magnifying glass. A dark filament is less dense than a cluster, but it's immensely long. Its cumulative gravity could, in theory, create a subtle, elongated distortion in the shapes of millions of distant background galaxies, not a dramatic arc. A statistical whisper, a slight, coherent stretching of galaxy shapes along an invisible line. Detecting that signal is like trying to hear one instrument in a symphony hall from a mile away. It requires surveying huge patches of sky with incredible precision, measuring the shapes of billions of galaxies, and looking for that faint, coherent warp in the data. No one has conclusively found a dark filament yet. The search is one of the great observational challenges now, but the hunt matters. It tests the limits of our models. It asks whether dark matter and ordinary matter always walk together, or if sometimes the dark skeleton can stand alone. Finding one would change everything. It would force us to redraw our maps, and it would remind us that for all we've learned about the luminous web, the universe's true framework might still hold secrets in the deepest dark. The gas in the cosmic web, it holds a history, a chemical record. So when we look at that warm, hot intergalactic medium, we're not just seeing hydrogen and helium. We're seeing a recycling program, the universe's recycling program. This is the ninth mystery, the composition of the filament gas. What it's made of tells you where it's been. Think about the first stars. They were pure, just hydrogen and helium from the Big Bang, but they were massive, short-lived. They ended in titanic explosions. Supernova, and in those blasts the furnaces in their cores forged new elements: carbon, oxygen, nitrogen, silicon, iron, all the elements heavier than helium. What astronomers call metals, and they were scattered into space. That was the first pollution, the first enrichment, and that process never stopped. Every generation of stars since has done the same, living, dying, seeding their surroundings with these heavy elements. But how do those metals forged inside stars end up in the filaments? The vast, empty-seeming filaments. The answer is in the winds, galactic winds. When many supernovae explode in a region, or when a central black hole is active, they drive colossal outflows. Hurricanes of hot gas, charged with these new elements, and they blow right out of the galaxy's gravitational grip. They launch this enriched material into intergalactic space. And once it's out there, it gets swept up. It joins the flows of gas moving along the dark matter filaments. It becomes part of the WIM. So the thin plasma in the filaments isn't just primordial. It's a mixture, a blend of the pristine gas from the beginning and the recycled ashes from countless stellar furnaces. That's why measuring the metallicity there is so powerful. It's like a core sample from an ancient glacier. Each layer tells a story. By analyzing light from a distant quasar as it passes through a filament, astronomers can detect the absorption signatures. The signatures of these heavy elements. They can estimate how much oxygen or carbon or neon is floating out there, millions of light years from any obvious galaxy. The results show something. The metallicity in filaments is low, but it's not zero, about 1/10 to 1/100th of the Sun's metal abundance, and that tells us two things. First, that process of galactic feedback, those winds blowing metals out, is incredibly effective. It has managed to pollute even the most remote corners of the web. Second, it tells us about timing. The level of enrichment suggests this has been happening for a very long time. Over many billions of years, the web has been slowly accumulating the byproducts. The byproducts of stellar life and death. This turns the cosmic web into a great circulatory system. It doesn't just structure matter, it mixes it. It takes the heavy elements, the building blocks of planets and organic molecules, and spreads them from the crowded cities of galaxies out into the intergalactic countryside. Later, when new gas flows into a filament and cools to form a new generation of stars and planets, that gas is already pre-enriched. It starts with a legacy of metals from earlier stellar generations. This recycling is fundamental. It means the iron in your blood, the calcium in your bones, the oxygen you breathe was likely forged in a star. A star that died long before our sun was born, and it traveled, perhaps for billions of years, along these invisible rivers of the cosmic web, before finding its way into the nebula that formed our solar system. The filaments are more than a skeleton. They are the vascular system for the chemical elements of life. The universe is full of these invisible bullets. Cosmic rays, they're particles, not light, mostly atomic nuclei, protons stripped of electrons and flung across space at almost light speed. Their sources are the most violent events we know. Supernova shockwaves, relativistic jets from active black holes. Once they're launched, these particles become nomads. They travel for millions of years, billions of years. And their journeys aren't random. They're guided by the invisible architecture of everything. The cosmic web provides the roads. A filament isn't just a river of gas and dark matter. It's a magnetic conduit, those faint magnetic fields woven into the warm, hot intergalactic medium. For a charged particle like a cosmic ray, a magnetic field is a guide wire. It doesn't stop it, but it bends the path, forces it to spiral along the field line. So when a cosmic ray is born in a galaxy inside a filament, its escape into the wider universe isn't a straight shot into emptiness. It's channeled. It spirals along the magnetic fields that are aligned with the filament structure. The filament becomes a pipeline, a highway system for high-energy particles, directing their flow along the dense threads of the web away from the voids. This channeling has a profound effect. It means cosmic rays aren't spread evenly throughout the cosmos. They're concentrated along the same pathways as galaxies. The filaments become enriched with these invisible high-energy travelers, and as they journey, they interact. A cosmic ray proton, moving at fantastic speed, can sometimes collide with a slow-moving proton from the sparse gas of the filament itself. That collision is a miniature explosion. It can produce other particles, and it can produce light, very high-energy light, gamma rays. This gives astronomers a new way to listen to the web. By pointing gamma-ray telescopes at the dark spaces between galaxies in a known filament, they search for an extremely faint, diffuse glow, a whisper of gamma radiation that would signal cosmic rays interacting with the filament's gas. Detecting that signal is like trying to hear a single conversation in a stadium from miles away, but it's a direct probe. It would tell us not only that cosmic rays are there, but how many and what energies they carry. This ties into one of the great mysteries: ultra-high-energy cosmic rays, the rarest, most powerful particles we detect. Each one carries the kinetic energy of a professionally thrown baseball, packed into a single subatomic particle. Their origin is unknown. They're so energetic that they should be disrupted by the cosmic microwave background over long distances. They shouldn't be able to travel far. And yet, we see them. So where do they come from? How do they get here? The magnetic highways of the cosmic web might hold part of the answer. Maybe the most extreme accelerators, the cores of certain active galaxies, or galaxy cluster mergers reside at powerful nodes in the web. When they fire out an ultra-high-energy particle, it doesn't fly blindly. The surrounding magnetic fields of the filament could focus its path. Like a fiber optic cable guiding a light beam, the filament could shepherd this incredible particle over a longer distance than would otherwise be possible, helping it reach us. By mapping the arrival directions of these rare events and comparing them to the large-scale structure, we might one day trace them back to a specific intersection in the great cosmic web. So the next time you look up at a dark, quiet sky, remember it's not quiet. It's humming with an invisible traffic of immense power. Particles from cataclysms across the universe, following roads we are only beginning to map, their faint signatures telling the story of the structure that guides them. The maps we have now, they're just rough sketches. The next telescopes, they're going to turn those into high-definition blueprints, and these aren't just bigger mirrors. They're new kinds of eyes, engineered to see the cosmic web not as a statistical ghost, but as a detailed landscape, something you can observe. The first one is already scanning from Chile. The Vera C. Rubin Observatory. Its mission is called the Legacy Survey of Space and Time. Over 10 years, it's going to image the entire southern sky every few nights. It won't just take pictures, it'll create a movie of the universe, catalog tens of billions of galaxies, measure their shapes and positions with a precision we've never had at that scale. And this map will be so dense, so comprehensive, that the filaments and voids of the cosmic web they'll just emerge, with a clarity that's stunning. We'll see the fine structure inside the threads. We'll trace how the web has evolved over the last few billion years. It'll find galaxies so faint, so distant, they were invisible before, filling in the gaps in how the web is woven. Now, while Rubin maps the present-day web in immense breadth, the James Webb Space Telescope peers into its infancy. Its infrared vision is perfect for looking back to the era of the first galaxies. When the web was just forming, Webb isn't built to survey huge volumes. It looks deep into tiny patches of sky, but in those patches it can see the faintest galaxies. The most redshifted ones, from the universe's first few 100 million years, and the critical question is whether those infant galaxies are already aligned. Do they trace the first faint threads of the primordial dark matter scaffold? Early data is already hinting at elongated structures, groups of early galaxies strung along lines. If Webb confirms this pattern at such an early epoch, it becomes a direct link, connecting the quantum seeds of inflation to the first luminous structures. It would show the Webb's framework was already in place, guiding the birth of the very first cities of light. But to see the web itself, the hot gas in the filaments, that requires a different sense. X-ray vision. Today's X-ray telescopes, they can only see the brightest parts of the WIM, usually where filaments feed into massive clusters. The future belongs to observatories like Athena. The Advanced Telescope for High-Energy Astrophysics, planned by the European Space Agency. Athena's huge collecting area and exquisite spectral resolution, that's a game-changer. It'll be sensitive enough to detect the faint X-ray glow from the warm hot gas in filaments far from any cluster. It'll measure the temperature, the density, the motion of that plasma. We will watch in real data how gas flows along these cosmic rivers to feed galaxy growth. An even more ambitious concept, a telescope like Lynx, would take this further. With vision 100 times sharper than current X-ray observatories, it could map the filamentary gas in stunning detail, see how it twists and interacts. Together, these new eyes will transform our understanding. They'll move us from inferring the web's existence to studying its physics directly. We'll measure how magnetic fields thread through it. We'll watch how feedback from black holes and supernova heats the gas within it. We'll see how the web's structure influences the spin of galaxies, the growth of their central black holes. This isn't just about filling in a diagram. It's about running a cosmic laboratory, testing our theories of gravity, dark matter, and galaxy evolution against a detailed, observable reality. The cosmic web is about to step out of the shadows and into the light, revealing the final chapters of how our universe built itself. The Milky Way isn't an island. It has a place in the larger structure. It spins inside a filament, part of the Laniakea supercluster. We're not in a dense knot of galaxies. We're not drifting in an empty void either. We're somewhere in between, a suburban street in the cosmic metropolis. And this specific location, this filament, has written parts of our own galactic story. It shaped the Milky Way's past. It set the stage for our existence. Think about the traffic. Our place in a filament means our galaxy hasn't been alone. Over billions of years, it's interacted with neighbors. It likely absorbed smaller dwarf galaxies. Their stars and gas merged with ours, building up the disk and the halo. Those mergers were driven by the gravitational flows along the filament. They were violent events. They triggered waves of star formation. Some of those stars, born in those ancient collisions, may have seeded the heavy elements that later formed our solar system. The iron in our blood might trace back to a galactic encounter, orchestrated by the large-scale pull of the filament we call home. Our location shapes what we see. The night sky from Earth is shaped by our place in the local web. The band of the Milky Way is our view from inside the disk, but the broader distribution of nearby galaxies, Andromeda, the Magellanic Clouds, that's a map of our local filament. We're embedded in a specific neighborhood. That neighborhood dictates the gravitational forces acting on us. It sets our future too. In several billion years, the Milky Way and Andromeda are destined to collide. A dance choreographed by the mutual pull within this shared filamentary thread. But maybe the most profound connection is to habitability. Could the large-scale environment influence the potential for life? It's a compelling thought. A galaxy in a dense cluster faces constant gravitational harassment, higher risks of disruptive close passes, intense radiation from numerous active galactic nuclei. A galaxy lost in a void might be too isolated. It may have consumed its gas long ago, becoming a quiet, aging system with little new star formation. Our filamentary suburb offers a potential middle path. A place with enough interaction to stir the pot, to enrich the gas with heavy elements, but stable and quiet enough over long periods to let planetary systems form and evolve undisturbed. The structure that governs the universe on the largest scales may have, through a cascade, played a subtle role in creating the calm, resource-rich neighborhood necessary for a planet like Earth. That realization ties the grandest scales of cosmology directly to the pale blue dot. The quantum ripples, the dark matter scaffold, the flowing filaments, they're not just a distant spectacle. They are the foundational history of our home. We're not just observers of the cosmic web. We are products of it. Our galaxy, our sun, our planet are all expressions of a pattern written at the beginning of time, patiently assembled over 13.8 billion years. To understand this architecture is to find our true coordinates. It fosters a deep, humbling sense of connection. To the vast, structured tapestry of everything, the universe looks like a fractal. It has this pattern, this branching quality. You see clusters, and inside those are groups, and inside those are galaxies. It feels nested, like it's repeating, but that's where the idea stops. The universe isn't a fractal. A real fractal, like a Romanesco broccoli, is self-similar. You can zoom in on a tiny piece and it looks just like the whole that goes on forever. The cosmic web doesn't do that. It has a scale, a preferred size. That size came from the initial quantum ripples from the Big Bang, stretched out by inflation. The filaments, the voids, they all have a typical dimension. A few 100 million light-years across. So if you zoom in on a galaxy cluster, you don't find a tiny cosmic web. You find stars and gas and planets. Different physics, and if you zoom out past that scale, the lumpiness fades. If you average matter over volumes larger than about 300 million light-years, the universe starts to look smooth. Homogeneous, the same in every direction. That's the cosmological principle. No special place, no center, no edge. The filaments and voids are like waves on an ocean. From a boat, the waves are all you see, but from an airplane, the ocean looks flat. The cosmic web is a ripple on the surface of a smooth, expanding sea. We observe this. Astronomers measure the clustering in galaxy surveys. On small scales, the clustering is strong. Galaxies are near other galaxies, but as you look at larger separations, that signal weakens. It drops off, it approaches zero, matter stops being clumpy, it becomes evenly distributed. The universe runs out of larger patterns, the fractal illusion breaks. And that tells us something about the origin. A truly fractal universe would challenge our understanding of the Big Bang, of the initial conditions. The transition to smoothness confirms the standard model. It tells us the universe had a definite beginning with specific properties, and it guides the far future. As dark energy accelerates expansion, those filaments will stretch and fade. But the underlying smoothness on the grandest scale will become more dominant. the ocean will calm and the waves will slowly disappear, so the cosmic web isn't an endless recursion. It's a finite pattern, a single grand chapter written on a smooth and uniform canvas. Gravity's pull isn't just some rule, it's the one thing you have to have for a cosmos with structure. To really see how special that is, you can flip it. Imagine a universe where the force between masses wasn't attraction, but repulsion, where every piece of matter pushed every other piece away. That's not just a different setting, it's a cosmos where structure never gets started. You could have the same starting conditions, a nearly smooth early soup with those tiny quantum ripples. But the moment those ripples try to grow, the physics works against them. A region with a slight overdensity wouldn't pull matter in, it would push it out. That extra mass would act like a repellent core, scattering everything around it. Any initial lump would get smoothed away, not amplified. The runaway process that builds galaxies in our universe would run in reverse, back toward perfect uniformity. There'd be no collapse, no condensation, no dark matter scaffolding pulling gas into rivers. Those vast flows that channel material along filaments wouldn't exist because every particle would be fleeing from every other. The cosmic web would be impossible. Instead of a tapestry of light and shadow, of dense knots and empty voids, this repulsive universe would become a featureless sea. Perfectly smooth, perfectly even, and perfectly dark. No stars would ever ignite because gas clouds could never gather enough density for fusion. No planets would form. No structures of any kind, from the biggest supercluster to the smallest asteroid, would ever come together. This contrast shows something. The attractive nature of gravity isn't a minor detail. It's the creative engine. It takes the faintest whispers of difference from the beginning and amplifies them into cathedrals of light. It turns randomness into pattern, uniformity into architecture. Without that persistent gathering pull, the universe would stay a formless cloud. The existence of the cosmic web, of galaxies, of us, comes from this one property. It's why the cosmos is clumpy and web-like and full of detail, instead of smooth and empty and simple. This attraction is the reason there's anything to see at all. The blueprint of the universe isn't just a scientific fact, it's a masterpiece. The cosmic web, in its scale and design, goes beyond data. It becomes art. When supercomputers run their simulations, they don't make charts. They create these images of breathtaking elegance. You see swirling rivers of gold and crimson, tracing the skeleton of dark matter. Luminous nodes of white and blue where the galaxy clusters blaze, and these vast spherical voids of the deepest black, all cradled by threads of light. These aren't photographs, but they are real. They're a translation of mathematical truth into a form our eyes can understand. And in that translation, something happens. The structure we see, it echoes forms we know. It looks like the branching network of neurons in a human brain. It mirrors a sprawling root system from an ancient tree. It recalls the delicate veins in a leaf or the spray of a coral reef. This resonance, it feels like more than coincidence. It suggests patterns, universal patterns of connection and growth and flow. Principles that govern the microscopic world within us and the macroscopic cosmos around us. So scientists and artists collaborate to bring this architecture into view. Data visualization experts work with astrophysicists. They use color not for decoration but for communication. Red for hot gas, blue for cooler streams. They use brightness for density. Three-dimensional rendering lets us fly through these structures to understand their depth and their scale in a visceral way. The iconic map from the Sloan Digital Sky Survey, with its millions of galactic points, it's a work of pointillism. On a cosmic canvas, each dot is a city of stars, and together they sketch a grand, sweeping form. A form the unaided human mind could never have conceived. These images, they do more than illustrate, they inspire. they evoke an awe that raw numbers can't. They remind us that the drive to understand the universe, it isn't a purely analytical exercise. It's a deeply human one. It's born from the same place as our appreciation for a landscape or a symphony. A longing to perceive order and meaning and beauty in the world. This intersection of art and science, it's essential. It makes the profound accessible. It lets anyone, regardless of their physics background, stand before an image of the cosmic web and feel its significance, to grasp intuitively that we are part of a connected whole. A whole of staggering complexity and harmony. The elegance hidden in the data is a reminder the universe isn't just lawful, it's beautiful, and in seeking to map its darkest corners, we are also inescapably creating a new gallery of wonders. A gallery that reveals the hidden artistry in the fabric of everything. The hidden artistry is now something you can touch. The principles that built the cosmic web, they aren't locked away in supercomputers. They're waiting for you to explore right from your screen. A new generation of tools brings the universe's grandest simulations to anyone curious enough to click. There's a program called Universe Sandbox. It's an open-source universe simulator, a cosmic sandbox, gravity, climate, collisions. It's all part of a real-time physics engine. You can start with a smooth cloud of particles, give it the tiniest nudge, an initial fluctuation, and then press play. Watch gravity take over, clumps begin to form. Filaments stretch between them, voids grow spherical. You aren't just watching a pre-rendered movie, you're conducting the experiment. You can change the rules. What happens if you increase dark matter? The structure forms faster, the knots become denser. What if you turn dark energy up? The expansion accelerates. You can watch the web stretch and thin before your eyes. It's a profound way to internalize cause and effect, the kind that took cosmology decades to unravel. For a quicker experience, many university cosmology groups host interactive visualizations. These are often based on actual data from massive surveys or their most famous simulations. You can zoom through a three-dimensional map of millions of galaxies, rotate it, highlight the filaments and voids with a toggle. These tools transform abstract concepts into intuitive understanding. When you manually adjust a parameter and see the cosmic web grow more pronounced or fade away, you grasp the fragility of that initial blueprint, the necessity of it. You become an active participant in cosmic discovery, not just a passive listener. This hands-on exploration does more than demystify. It empowers. It turns the awe of a distant image into a deeper satisfaction. The satisfaction of comprehension. You're not merely being told why galaxies gather along filaments. You're watching the universe itself follow the recipe. And you're holding the spoon. This accessible journey makes the architecture of everything feel less like a remote secret, more like a shared story, one we are all now equipped to read. The universe has this economy. Its currency is matter, and the trade routes are the filaments of the cosmic web. You can think of the old networks, the Silk Road, or a modern highway system. The filaments do that, but the scale is different. A single city on that web is a cluster of 1,000 galaxies. These are gravitational highways. They're the supply lines. Where the highways meet, you get the metropolis. That's a galaxy cluster, a dense hub. That's where the trade is most intense. Gas flows in from all directions. That's the raw fuel for making stars. And the galaxies themselves, they get pulled in by the gravity. They travel these routes into the crowded node. Sometimes they merge, huge deals that change everything. The cluster gets rich from that constant influx, but the highways themselves, they're active too. Towns spring up along a freeway. It's like that. Smaller galaxy groups, individual galaxies, they form along the filaments. They're not as grand as the central city. But they're connected, they have access to the flow, they can intercept passing gas clouds or interact with a neighbor that can spark new stars. Their growth is fueled by the traffic. What's being traded? The main resource is the gas, primordial hydrogen and helium. That's the bulk commodity. It flows from the empty regions toward the dense wells. But the cargo is more than that. There are the metals, the heavy elements made inside stars. When a galaxy has a burst of star formation or an active black hole, it can expel that enriched material. That pollution gets picked up by galactic winds. It goes into the filament. It becomes part of the traffic. So later, when another galaxy farther down draws in gas from the filament, it gets more than raw fuel. It gets pre-processed materials, seeds for planets, for complex chemistry. The filament is a distribution network for the building blocks. This explains a principle of location. A galaxy alone in a void is like an isolated village, no roads, it's cut off from the economy. It probably used its initial resources long ago. With no new deliveries, its star formation stops. It gets quiet, it ages in isolation, but a galaxy on a filament is part of the marketplace. Even if it's not in a dense cluster, it's connected to the flows. It has opportunities for growth, for interaction, for receiving new materials. Its long-term evolution is shaped by that connection. The analogy makes it tangible. We see maps as static, but they're not. They're diagrams of motion, of exchange. The cosmic web isn't just where things are. It's how things move. It's a living circulatory system. Where you're placed within it determines almost everything about your destiny. This gravitational economy built the galaxies, and it keeps shaping their futures. One slow transaction at a time. The universe has a voice. We're learning to listen. There's another way to experience the cosmic web beyond the maps and the simulations. Through sound, it's called data sonification. It takes the silent architecture of everything and turns it into a symphony. It starts with the same datasets. The three-dimensional coordinates for millions of galaxies. But instead of plotting them as points of light, you assign each galaxy a musical note. The position along a filament could set the timing. The density of galaxies might control the volume. The distance from Earth could shift the pitch. A sparse, lonely void becomes a deep, resonant silence. A dense knot of galaxies where filaments cross swells into a powerful chord, rich with overlapping tones, and as you move along a filament, the notes rise and fall. They trace the hills and valleys of that gravitational landscape. You're not just seeing the structure, you're hearing its shape. This is more than a novelty. It's a tool for discovery. Our eyes are good at spotting certain patterns, but our ears are tuned for sequences, for rhythms and harmonies. A subtle trend in the data, something you might miss in a visual graph, can become an obvious musical motif. A repeating cadence in the notes might hint at a regularity, a pattern in the spacing of galaxy clusters. An unexpected dissonance could point to an anomaly. A region where the data doesn't fit the model. Sonification offers a different kind of perception. It engages another part of the brain to find meaning in the numbers. And it opens the cosmos to new audiences. For the visually impaired community, sonified data turns an inaccessible image into an experience. The grandeur of the cosmic web, once just pictures, can now be felt as a vibration. A melody, a spatial soundscape that unfolds over time. It embodies a principle that scientific understanding should be for everyone, that the wonder of the universe isn't locked behind a single sense. Projects like the System Sounds Collaboration or work at NASA Chandra X-ray Center, they create these cosmic compositions. They take the X-ray glow of a galaxy cluster, the light curve of a distant star, the map of a filament, and they give it a voice. The results are haunting, beautiful, strangely intuitive. They remind us the language of the cosmos isn't just light and mathematics. It's also pattern and relationship. And sometimes, to understand the deepest truths, you have to close your eyes and simply listen. That shared story of connection makes you ask a final question. With all this knowledge about our place in the cosmic web, what is our responsibility? In a world with so many needs, why look up? The pursuit is a deep expression of who we are. It answers a basic drive to know where we came from and where we are, to find our coordinates in the grand scheme. This search for context isn't a luxury. It's a core part of human identity. When we map the filaments that formed our galaxy, we aren't just doing astronomy. We're reading our own origin story written across the sky. That shared narrative, the realization that everyone lives under the same cosmic architecture, it fosters a sense of unity, a global perspective from the grandest scale. It cultivates a deep humility. Our conflicts and divisions, they shrink against the backdrop of a web 13.8 billion years in the making. This cosmic perspective is a gift of scale. It lets us see our world not as an isolated stage, but as a single, precious point within an immense, structured void. That vantage point can inspire a new kind of stewardship. When you comprehend the staggering emptiness between the filaments, the rarity of a stable, life-bearing planet like Earth becomes achingly clear. Our planet is not just a habitat, it's an oasis of breathtaking complexity, adrift in a vast desert. This knowledge doesn't pull us away from our challenges. It reframes them. It highlights the fragility, the irreplaceable value of our only home within the silent grandeur of the web. And the resources for this pure quest for understanding, they yield tangible rewards too. The technology forged to peer into the cosmic web, advanced sensors, data processing algorithms, precision optics, it finds its way into daily life. Medical imaging, communication networks, materials science, they all benefit from these innovations born of cosmic curiosity. The drive to comprehend the universe's architecture becomes an engine for progress right here. So studying the cosmic web matters because it answers a deep human need for meaning. It provides a context that can unite us, it fuels innovation that serves us, and it offers a perspective that can guide us. To look up and trace the filaments is to take the most human of journeys. A journey to find our place, and in doing so, to better care for the fragile, glowing point we all call home. We've mapped so much, but the biggest structures, they're still hidden. The cosmic web rests on two things we don't understand: the invisible skeleton, dark matter, and the force stretching it thin, dark energy. We know what they do with incredible precision. But what they are, that escapes us. What is dark matter? We can trace its gravity across billions of light years, but we've never directly caught a single particle. Our most sensitive detectors, buried deep underground, they hear nothing. Is it some new, exotic particle? That's what a lot of theories say. Or maybe it means our understanding of gravity is wrong on the largest scales. The web's architecture is built from a material we can't touch. Its main architect is a ghost. Then there's dark energy. The discovery that the universe's expansion is speeding up, that was a shock. It means there's some energy woven into space itself, a kind of anti-gravity pushing everything apart. This force decides the web's ultimate fate. As dark energy's influence grows, it'll stretch the filaments. Drain them, maybe over trillions of years, sever the connections between galaxy clusters. But what is it? Is it just a constant property of empty space? Or a field that changes over time? The answer tells us whether the web endures as a faint trace, or dissolves into a cold, smooth void. Our view also hits a horizon. The observable universe is a bubble centered on us, limited by the speed of light and the age of the cosmos. We can map the web inside this bubble, but outside. Could there be structures even more immense, patterns on scales we can't conceive? Is our cosmic web just one thread in a superstructure of unimaginable size? We may never know. The universe keeps its biggest secrets hidden behind expanding space and time. This isn't a failure of science, it's its greatest strength. Our models of the cosmic web are breathtakingly successful, and yet they're incomplete by design. They're maps that work with blank spaces labeled, "Here be dragons." That humility, that acknowledgement of the unknown, that's what pushes discovery forward. Every time a telescope confirms a filament or a simulation matches an observation, it doesn't close a book. It opens a door. Behind it are deeper, more subtle questions about the forces that sculpted all this. The cosmic web isn't a puzzle to solve and set aside. It's a living field of study, a conversation with the cosmos that's lasted centuries and will last centuries more. Each generation's answers become the next generation's questions. And the wonder of tracing our place in the grand design that never really ends. The universe isn't just a random scattering of lights, it's a structure. A tapestry. Every galaxy we see, every filament we map, it all comes from a chain of events that started at the very beginning. Gravity's pull, guided by dark matter, by those faint quantum seeds, it spent over 13 billion years weaving this web. This web of light and shadow, galaxies gather along filaments, and that's not an accident. It's the outcome, the cosmos following its own rules. These are the gravitational highways. The natural channels where matter flows, condenses, and ignites into stars. From finding the missing ordinary matter in the hot gas, to seeing how a galaxy's spin remembers the direction of ancient cosmic rivers, each discovery peels back a layer. It shows an architecture, an elegance, an interconnectedness. So next time you're under a dark sky, look up. You're not just seeing isolated specks against a black emptiness. You're glimpsing the luminous threads of the largest structure we know. You're seeing the bright traces of the cosmic web, the scaffold, the enduring scaffold everything is built on. That perspective, it can fill you with awe, it can spark curiosity.